Hello. So, we resume again with our sixth lecture of the series on tectonics and geodynamics. So, this time we are going to talk about how plates would move on a flat earth. So, before we proceed a little bit further, let us actually go on to what exactly we are going to deal with, the concepts that we are going to cover in this particular lecture. Up to now, whatever we have done is to explain how the theory of plate tectonics evolved, and it was more of a story that I told you. So, this was a very interesting story, a story that actually defined how the solid earth geosciences have evolved primarily over the latter part of the last century. And today, most of the things that we try to interpret on earth, on the solid of processes happening on the solid earth, have to actually do with processes that are involve plate tectonics. Now, these types of things, actually, to understand the geometry of how plates actually move, we need to have some idea of how things would geometrically happen if they happened with irrespective of whether they are moving on the surface of the earth or whether they are moving on a flat surface. So, we have to apply very basic concepts of essentially high secondary level physics. Nevertheless, we would need to understand exactly what happens, but sometimes they can come up with counterintuitive implications, which is important for us to understand when we are looking at plates on the earth's surface and trying to understand how the geometry of plates actually evolve on a flat earth. So, let us just get back to where we were, in the last segment. So, this again is a map that shows essentially the seafloor topography, and it is from the National Geographic. This particular figure actually is something that shows you the positions of the continents and the oceans, and if you remember that I like this figure because it actually seems to show all the plate boundaries as physiographic features on the surface of the earth. Now, essentially this is very good for the oceans because you can actually see it in terms of how the oceans have been evolving. So, you can see the mid-oceanic ridge passing from right through the middle of the Atlantic Ocean. So, it passes through what is Iceland here, and then it passes through the middle of the Atlantic Ocean right through from this part here, separating South America and Africa. And if you recall, it's a brilliant replica of the western coast of Africa and the eastern coast of South America. So, this particular part is simply the part that is still retained in the Atlantic Ocean, and you can reconstruct the geometry from here. Now, you have got a small little trench zone here. This is the South Sandwich Trench, and you have got another small trench here, right. This is the Lesser Antilles. So, together with these, you have the ridge system passing on into the Indian Ocean. So, this is the Indian Ocean triple junction, from which we have the Central Indian Ridge, the Southwest Indian Ocean Ridge, and the Southeast Indian Ocean Ridge, right, that passes through here. Maybe what I will do is, for this part, I will choose a red pointer because it is a little clearer for you to understand. So, what you can see is this particular part is the Indian Ocean triple junction where these plates meet. So, what you have actually got is a separation between these plates. Now, as this ridge system continues through here, right, it passes right through into the Pacific Ocean here. It is displaced across numerous transform faults. Note again that these transform faults appear to be arcs of small circles on the surface of the earth, and you have a set of other ridges that passes through here. There is another ridge that passes through this particular segment. And then you of course have the famous trenches of the Pacific Ocean, which define the Pacific Ring of Fire. So, all of this is the Aleutian Trench. Then you actually get into the Japan Trench, you have the Mariana Trench, right, and you have all of these other Luzon Trench and all of these passing through here. You have even got the trench in that passes right through Indonesia, from the south of Indonesia into the Bay of Bengal, passing into the eastern part of northeastern part of India, and then finally the part that is now a collision zone, that is the Himalayas, passing in fact into the Alps. So, you also have subduction zones in the Mediterranean Sea. So, you have a whole segment of transform faults and subduction zones, right, passing through, dividing the earth's surface into a series of very rigid plates. Now, this is just again to help you recall what these plates were, so which we've actually retraced for you. Now, once again, just remember the names of the major plates. So, you have the North American plate. The North American plate comprises the almost the whole of the North American continent, right, and the western part of the Atlantic Ocean. The eastern part of the Atlantic Ocean, the northeastern part is supposed to be a part of the Eurasian plate, whereas the part that's to the south is a part of the African plate. You also have the South American plate, which includes most of the South American continent along with the western part of the South Atlantic. Okay, and this separates it from the African plate, which is here. The African plate itself, note, is surrounded mostly by ridges. And there are suspected new boundaries forming in places, but we are not completely sure about the status of these. These are all diffuse boundaries which are probably developing, but in all, most of the African plate is actually surrounded by ridges. You actually have only a small segment to the north which actually has trenches, and these are the trenches the famous trenches of the Mediterranean Sea. So, you have parts where the ridge system actually passes into the Red Sea and then it converts into a transform fault. This is the Levantine transform system here. Now, the ridge, the Indian plate, the continent we live on, right, that includes the whole of peninsular India right up to the base of the Himalayan foothills, right, and it includes most of the Arabian Sea and also of the Bay of Bengal, and it stretches as far down as here. Previously, this was considered to be a part of a single plate, but now we think that there is a zone of diffuse stretching where we think a new plate called the Capricorn plate is actually coming into being. So, this is actually a separation that we think of between the Indian plate and the Australian plate. So, they are no longer considered to be part of the same plate. Likewise, the original plate configuration did not realize that there was a Somali plate separating the Indian plate from the African plate, but now we have the recent ideas seem to indicate that we think there might be a Somali plate out here. The Pacific plate is in fact the largest plate, but if you note the boundaries of the Pacific plate, it does have ridges, but a very significant part, right, of the Pacific plate is actually surrounded by trenches. And the Pacific plate, likewise, I mean, that is the reason why we think the Pacific Ocean, which is majorly occupied by the Pacific plate, that is actually decreasing in size over time, because the amount of trenches that you have in the Pacific Ocean actually tend to bring all the plates together. They tend to consume all the plates and reduce the surface area that is occupied by the Pacific Ocean. In contrast, the Atlantic Ocean, which includes several plates, the Eurasian plate in the north, the African plate here, the South American plate and the North American plate, this has only two subduction zones. One is this one in the Caribbean zone, which is the Lesser Antilles, and you've got the South Sandwich Trench, which is here. So, these are the only two places where the Atlantic Ocean is actually being consumed. So, otherwise the Atlantic Ocean is simply spreading apart, and it's actually moving away from this region along this part here and this region here. So, as a consequence of which the Atlantic Ocean is still actually growing. So, you can see that the surface area that is occupied by the plates, right, is not steady state. These are changing with time and they increase or decrease, and that is why we can see a change in the geometry of the distribution of the continents on the surface of the earth. When we look at the surface of the earth, the bulk of it is actually occupied by the oceans, but there are parts that are occupied by the continents, which are the ones that are easily identifiable to us. Now, this tells you about the geometry of what occurs on the Earth's surface, right, and this is how the spherical image has been projected onto 2D just for convenience of vision. But let us just now take one look back at exactly how the plates are operating, what kind of stuff are we looking at. So, this is just a very rudimentary cartoon trying to recall once again the nature of the processes that are going on. So, let us just start off here. There is an ocean here. So, even if these two continents, let us imagine that there might have been two continents together which have been split apart at the mid-oceanic ridge, which is round about here. So, the mid-oceanic ridge itself, the mid-oceanic ridge here, right, it spreads apart. So, you actually have forces pulling the lithosphere apart here. So, new oceanic crust and new oceanic lithosphere is being generated at these points here with associated earthquakes. The ridges are occasionally displaced by these transform faults. So, you can see a transform, this segment of it is the transform fault. This is the only region where there are earthquakes along the transform fault. So, although you have the scarp continuing beyond this, there are no earthquakes in these regions. So, the earthquakes are actually confined to the region between the two ridge segments. So, the ridge segment continues across here and then across here. So, the boundary between these two plates essentially follows this part, and the earthquakes, the seismicity, the volcanism actually is confined to this particular region. So, all the region right to the west of this red line that I have drawn is part of one particular plate. All the region to the right of this line is part of another plate. So, you have the crust as well as the lithosphere together making up the lithosphere. So, the plate itself. So, the plate itself you can actually think of it as being something a little bit larger here. So, something that comes in through here. So, the lithosphere grows as you move away from the trench. So, you just modify the image a bit. Now, as soon as the lithosphere splits apart, so you have new ocean magma rising to form the new ocean floor. We will talk about these things later. But then let us look at these two types of boundaries. Now, once again recall the two types of ocean continent boundaries we have, right. So, you could have one part which is a subduction zone. We have shown schematically shown two different types of subduction zones here. One is where two oceans come into contact. So, this is also an oceanic plate, this is an oceanic plate as well. Both of them are converging. So, this is a boundary, this is the trench which marks the boundary between these two plates. This is an oceanic plate, this is another oceanic plate, and we have got this oceanic plate subducting below this one. So, this oceanic plate, right, the one which is subducting, this is referred to as the subducting plate. The plate, right, which is not subducting, right, which lies above the trench, this plate is referred to as the overriding plate. So, we have them separated by a trench. Now, the trench itself, even on the surface of the earth, is arcuate in shape, and you have a line of volcanoes, right, which are parallel to these to the trench itself. These actually define what we call the island arcs. So, this is the configuration we normally see when you have ocean-ocean subduction zones. The lithospheric plate dives down, the subducting plate goes down this way. Earthquakes are concentrated at the tops, sometimes also some earthquakes at the bottom. Most of them would be along the top of the subducting plate. All of these parts within the lithospheric plate that is subducting, these are colder than surrounding parts. So, they are actually more brittle. As a consequence, they can transmit stresses faster, which is the reason why you actually see all these earthquakes occurring, which help us to trace the plate as it goes down. So, this is what constitutes my Benioff zone. So, magmas are generated as the plate subducts, right. We will discuss the reasons why this magma is formed, and the magma that is formed comes out and erupts on the surface as lavas here, which characterizes our island arc volcanism. Now, the other type that you could have is that the overriding plate, in this case, this is also an overriding plate, but this overriding plate is continental. So, here you have an ocean continental margin, right, along the plate boundary. Again, this is my trench. Again, it should be normally it should be arcuate, but it is not necessarily so, because the front surface is actually defined. The front surface of the position of the boundary would be defined by the frontal edge of the overriding plate. So, this is the overriding plate. So, the frontal edge of the overriding plate here and the frontal edge of the overriding plate here, these actually define the location of the plate boundary. So, this plate and this plate are separate plates. So, you have actually got in this diagram, you have got, let us say if I call this plate A and I call this plate B, then this is plate C and this is plate D. Now, so you have got a whole sequence here. In this case, the continental plate, right, you would have subduction occurring, exactly the same processes that you see here would be occurring here, except that now you have continental crust on top. Here you had only oceanic crust. So, the continental crust, once again you would have magma being generated. You would actually have eruption of volcanoes on the surface. These would form what we call the continental arc. Okay. So, there are positions respect to this that we will discuss this in greater detail when we approach it, but this is the broad kind of geometry that goes on. Ultimately, what actually forces all of these things to happen is convection in the mantle, but as we will discuss later, convection in the mantle is largely driven by the motion of the plates themselves, and there is a particular reason why this happens, why plate motions themselves actually drive the kind of convection that we actually see. So, now I have told you about the processes, I have showed you the geometry as it actually exists on the surface of the earth. What we now need to do is to understand exactly how plates would actually move among themselves, right, how they would actually move among themselves if we were looking at these plates on a flat earth. Now, to understand, right, how this happens, how do we actually begin to analyze this? First of all, we will imagine that all of these plates are boundaries that are flat. Let us imagine that we are not talking about a spherical earth at all, we are just talking about plates on some surface area which is occupied by a large number of rigid plates. Now, we know that there are, let us say, 3 types of plate boundaries, 3 types of plate boundaries. Pardon my handwriting, it is never been good and I have had complaints from all my teachers. However, I will try to write them as clearly as I can for the 3 types of plate boundaries. So, the first one is divergent. Now, the conventional way in which I am going to show this divergent boundaries, the second one is convergent, and then of course, the third one is conservative, which is the strike slip one. Now, whenever I am actually showing these, depicting them in symbols, I am going to actually now draw diagrams in 2D just to show you exactly what these types of diagrams, what these types would indicate, now the way we actually depict it here. So, for these now, maybe I should shift, it is better if I shift to a black color just to make, just for variety. So, the divergent boundary, conventionally we actually show it in 2D. When we are trying to show a divergent boundary, we depict them as a set of parallel lines which are close to each other, and then we have these 2 arrows which are exactly equal in magnitude, but opposite in direction. Now, these represent vectors, they actually show you the movement vectors. So, these would be the rate. So, new oceanic crust lithosphere is being created along here and it is spreading out to this side and that side. The magnitudes must be identical because this is the same ridge. So, we now measure the velocity. So, these would be 2 different plates A and B. So, this ridge, this mid-oceanic ridge is actually separating 2 plates, and these plates are being depicted as a set of parallel lines, right, and the parallel lines are characterized by boundaries which are actually moving away from the 2 plates. Now, although it is not necessary, we generally try to, or it is generally seen and it is generally the case that the spreading direction is orthogonal to the trace of the boundary. So, this is the boundary itself. So, normally the way the ridge spreads is at right angles, we assume it is at right angles to this part. Now, it need not necessarily be the case, especially say when a continent is being pulled apart ultimately to create a new plate boundary. In the initial phases, it may not actually be completely perpendicular to the trace of the boundary. So, there may be a significant component. So, it might be something like this, which means there would be a component which is divergent and a component which is parallel to the trace of the boundary, which means that there is an element of strike slip movement also along the boundary, which we can actually now characterize by the word transtension. Now, these are complicated terms, these are terms which we will be coming across from time to time. Nevertheless, when we are trying to understand the geometry of plate motion, now initially we will assume that in most cases, and this is actually generally true, that the spreading across a mid-oceanic ridge normally takes place orthogonal to the ridge trace. Also, they are always equal in magnitude, but opposite in direction. So, now if I take any 2 points, right, on these 2 plates, right, let us say this is, we treat these in terms of centimeters per year. So, these are related in centimeters per year, let us say, right. So, in each of these cases, if it is related in centimeters per year or millimeters per year, then the rate at which these are created would be, say, at the rate of 1 to, it can vary from less than 1 centimeters to greater than 10 centimeters per year. Sometimes there have been postulates that there could have been some ridges which actually spread at 20 centimeters per year. But then that would mean that if the rate at which new crust on lithosphere being created here is x, then this is x as well, which then means that the relative velocity between these two plates, would actually be 2x. So the magnitude would be 2x. So therefore, we use a term in the context of divergent boundaries, we use a term called the half spreading rate. Now, this is the rate at which new lithosphere is being created here. So, the relative velocity between the two plates on either sides of a mid-oceanic ridge would be that is, the spreading rate would actually be twice the half spreading rate. So, this is something that you have to keep in mind. The half spreading rate and the spreading rate across two plates separated by a ridge, right, would have to be twice the rate at which the lithosphere is being created. So, this is the standard way of depiction in 2D of a mid-oceanic ridge, of a divergent boundary. Now, what about a convergent boundary? Now, the depiction is different. So, we show it. So, let us say the convergent boundary, we show it, let us say, as a line. In 2D, it is just a line. So, the way it is marked out is that you will have boundaries like this. Again, the two lines, these represent vectors. So, they would be exactly equal in length, which represents the magnitude. And although the magnitude is the same, note that now the directions are towards each other, unlike in the case of the ridge where they were acting away from each other. Here they are pointing towards each other. Now, this particular thing also means that you can actually have it at an angle like this, in which case there would be a significant strike slip component as well. If such a thing happens, and such things do happen fairly commonly, we then refer to these as transpressional boundaries, where there is a significant component of strike slip transform movement combined with the compressional movement that compressional stresses that you see. So here you would have cases which are strike slip, but for the time being now, let's actually not think of this part here. So I'm just erasing it for convenience. Let's just look at the part that we are talking about here. So we again, let's call these plates C and D just for convenience now. So here plates C and D are converging. Now this is enough to tell you that this is a convergent boundary. It could be a subduction zone, right? It could be an ocean continent subduction zone as well. It could be an ocean subduction zone. It could even be a collision zone. However, the full information is not actually being conveyed here, because there are two things that are associated with a convergent boundary. And the two plates, there is a polarity. This is the term that we use. There is a polarity associated with subduction zones, which is not the case with a mid-oceanic ridge. That is, the two plates are not identical. In the case of a subduction zone, one has to be subducting, the other has to be overriding. Now, if this is the case, right, if this is the case that is being shown here, and plate C, let us call this plate C, is subducting below plate D, right. In that case, this is the trench, so this is the mark that you see here. So plate C is subducting below plate D. How do we show it in 2D? So in plan view, the standard way of depicting this is with a set of actually filled triangles. So if you look at books, normally they would actually fill in these triangles in black, right. So this actually indicates that C is the subducting plate, D is the overriding plate. So the arrows, you can think of the vertices of these small triangles, these are pointing in the direction of the overriding plate. So these are pointing in the direction of the overriding plate. Now the position of the convergent boundary, is marked by the position of this particular line here. So wherever the frontal edge of the overriding plate is, that is the position of the convergent boundary. That is the position of the convergent boundary. So, in this case, this is how you would show it. Now, what if it was just the opposite? Plate D was subducting below plate C. So, you would have, I am talking about a case like this, right. So, you would have a case here. So, this is plate C, let us say this is plate D. Now, you have got the same thing, right. Both of them are pointing towards each other, right. Again, it is the same convergence zone, but the situation is different. Now, plate C is the overriding plate and plate D is the subducting plate. In this case now, you draw the same line, you would have C and D, you would have the same two arrows, right, with the same two lengths if the magnitudes are the same, but in this case the arrow, the triangles will point in the opposite direction. So, the set of triangles that you see here, right, that you mark out on the line, they will point in the direction of plate C, because the vertices will point in the direction of plate C, because C represents the overriding plate. Now, what about the conservative plate boundaries? Now, these are what we call transform faults. These are my transform faults. Now, these transform faults, how do I actually depict them on this kind of diagram? Once again, we have to show them as a line. So, let us say we have a line like this. Now, in this case, let us say this is plate E, this is plate F. Now, I am just using different letters just so that we do not mix all of these up. So, let us say plates E and F are separated now by strike slip boundaries. Now, plates E and F, if they are separated by strike slip boundaries, right, you would actually tend to have boundaries, right. You can actually depict them moving this way with respect to each other. So, when I say when I am I was always a poor artist, and you can see it here. So, I will just draw it as a pair of lines, right, which is actually showing half arrows pointing in opposite directions in either of the two plates. Now, this means that to any observer on plate F facing the transform fault, so on any observer on plate F who is facing the transform fault, in this case, any person on any object or any person on plate E will appear to move to the right. Okay. Similarly, if any person is standing on plate E, right, and observing the other person on plate F, to that person also plate F, the person on plate F will appear to move to his right. In that case then, no matter which way you are viewing it, to an observer on either plate viewing the fault, right, they will viewing the other or the opposite plate, he or she will observe the other plate moving consistently towards the right, whether you are an observer on plate E or an observer on plate F. Alternatively, you could have a situation which is just the exact opposite, right. So, in this case, an observer here and an observer here, right, would observe, an observer here facing the fault would observe the plate on the other side moving to its left. An observer here on this particular plate would observe an observer on plate E moving to the left. So, you will get left on both sides. For both cases, you will have movement of the observers to the left. It is consistent. Now, these represent, this is the standard notation we use to depict transform faults. So, transform faults themselves can actually be depicted this way, but we have to differentiate between the two senses, the two types of movement that we see in these two types of transform faults. So, in the two types of transform faults, the movements we have would actually tend to indicate different kinds of motion. So, if you have a transform fault on this side, it indicates that the person, when the person is moving to the right, you can call it a right-handed transform, or this right-handed transform fault, the standard terminology we used is to say that this is a dextral transform fault. This, on the other hand, is left-handed. So, the term that we use here is that it is a sinistral transform fault. So, you have a dextral transform fault and you have a sinistral transform fault. So, two different types of transform fault to differentiate between divergent, convergent and conservative boundaries. Now, let us just think of how we would actually show these as velocity vectors in two dimensions. So, let us say we have velocity vectors and we have plate boundaries in 2D. We can actually depict these in different ways. So, let us now just think, right, that we have got, let us say, a very hypothetical situation. Let us say we have got a plate A, which is completely surrounded by another bigger plate B. Mind you, mind the words hypothetical, this is a 2D thing. So, I am just actually now showing you two plates, right. One plate separated completely, it is, as you can see, it is just a square to rectangular figure, right, which is enclosed within another plate, plate B. So, these boundaries are the boundaries between plates A and B. Now, let us just imagine, right, that the western boundary of plate A is this one, right, and we have this as a mid-oceanic ridge. So, this particular boundary, the western boundary between plates A and B, we will treat it as a mid-oceanic ridge. This mid-oceanic ridge, let us say that it has a half spreading rate of 2 centimeters per year. Okay. It has got a half spreading rate of 2 centimeters per year. So, now if there were two observers here and here on these two plates, they would observe, an observer on plate B would observe the observer on plate A to be moving towards east at the rate of twice into 2, that is at 4 centimeters per year. Now, the way we depict this, we say that the relative velocity of plate, let us say plate A relative to an observer on plate B, right. So, this is, we show typical vectorial notation, in this case would actually be equal to 4 centimeters per year, right. So, we can also just write it 4 centimeters, I can also use this terminology, right, just to this symbol to actually show you how the plates are moving apart. So, this would be the half spreading rate here. Now, what consequences would this have, right, for the rest of the boundaries? Now, the geometry of the boundary is fixed. Now, I have already drawn in the geometry. To find out what the nature of these boundaries would be, right, let us just quickly look at what these boundaries might represent. Because these two are rigid, every point on plate A, right, must be moving with the same velocity with respect to plate B. Likewise, for every point on plate B with respect to plate A. So, every point on plate A is being generated here and moving on this side. So, what would you say? The boundary here would move this way, the boundary plate B on that side would move this way. So, now you would get the two boundaries, the one to the north and the one to the south. Here the velocity vector is 4 centimeters per year. That means the relative velocity vector would actually be a line twice the length, it would be of 4 centimeters. So, this would be 4 centimeters in length, right. This would be the relative velocity of A with respect to B. So, if this was B, the person on B would observe A to be moving at the rate of 4 centimeters every year, right, to the east. Now, therefore, along this boundary, we can see that the orientation of this particular boundary is exactly parallel to the velocity vector. If I use a different color here, just to make it easier. So, this boundary here, you can see that the person on plate, the person who is actually on plate B will observe plate A moving right at 4 centimeters per year. The person here would observe plate B moving westward at 4 centimeters per year. Now, this means then the boundary, then this particular part would be a transform fault, but because you can see that the velocity vectors are exactly parallel to the orientation of the plate boundary. Now, let us go to the southern boundary. Here also it is the same, the orientation of the boundary is exactly parallel to the velocity vectors. So, the velocity vectors would be like this. However, the velocity vectors, sorry, it is just here. So, the velocity vectors here also, this part, the boundary would actually move this side, and here the boundary would move this way. Now, if you look at the northern boundary, right, if you look at the northern boundary between plates A and B, you can see that plate B is moving to the west with respect to plate B, to the left in other words. So, this part is a sinistral transform fault. If you look at the lower boundary, you will see that plate A is moving to the right with respect to plate B is also moving to the right with respect to plate A, which means this is a textural transform fault. What about this boundary now? Once again now the velocity vectors are here, right, and now the velocity vectors, you can see that every time the arrow, the relative velocity vector has to have an arrow which actually points consistently at every point with respect to A. So, every point on A would be an arrow with the arrow pointing this way with respect to B. Every point on B would be an arrow which represents the relative velocity of B with respect to A. Now, what we are observing here is that both these arrows are pointing towards the boundary. It means that every point on plate A is moving towards this boundary, every point on plate B is also moving towards this boundary. This means that this particular boundary, this boundary here, must be a convergent boundary. Now, if this is a convergent boundary, right, we know that this convergent boundary could be of two types. One is plate B, the plate B could be the overriding plate. Now, if plate B is to be the overriding plate, then we have to show this, as a series of triangles like this with the apices pointing towards plate B. This means that plate A is subducting below plate B, right. The alternative, of course, the alternative is that if I just rub this out, sorry. So, if I just go here and I just okay, I will just choose the black one again. Let us just go here and we think of an alternative situation. So, I am just drawing plate A again here, just to show you what would happen if plate A was the overriding plate and plate B, right, is the subducting plate. This is how you would show it. So, in this case also the arrows would remain the same, they would be of 4 centimeters length, and this is what you would see. Now, just to conclude today's class, what would be the consequences if we had something like this? Let us say if we had plate A, right, showing this kind of geometry with respect to plate B. So, it is being produced at the rate of 2 centimeters per year here, right. What would happen to this place if you came here next year? What would you see? Now, if let us take the first situation here where we have plate B, right. No, let us take the lower one first. This is actually easier to think of. This is plate A is the overriding plate and plate B is the subducting plate. If this is the case where plate B is the subducting plate, in that case then, right, along here every year, right, this is the boundary here, right, you have got the transform faults here, right, and you have got the subduction zones here, right. So, this is 2 centimeters per year, but these are all 4 centimeters per year. So, now what would happen here? We know along this boundary, right, the frontal edge of this boundary, the position of this particular trench, right, this is actually specified, this position of this trench is actually specified by the frontal edge of the overriding plate. In this case, the overriding plate is A. Now, the line of points that is marking the frontal edge of point A is not changing with time. A is being produced at the rate of 2 centimeters per year. So, overall this particular boundary will also keep moving eastwards at the rate of 2 centimeters per year. So, every year plate A is going to elongate, right, by 2 centimeters per year. So, with time plate A is simply going to grow in size, it will grow at the rate of 2 centimeters per year. Let us just think of an alternative situation, the alternative where now the plate A is the subducting plate and plate B is the overriding plate. That is this diagram here. What would happen in this case? Now, in this case, this is something interesting. Plate A is still being produced at 2 centimeters per year. So, it is actually trying to move at 2 centimeters per year eastwards. However, along this trench, consumption of plate B, subduction of plate A is taking place at the rate of 4 centimeters per year, because that is the relative velocity between plate C and B. As a result, every year 2 centimeters of plate A are being consumed. 2 centimeters of plate A are being consumed every year. So, which means next year if you come here, plate A will be shorter, smaller by 2 centimeters. Next year it will be smaller by even 2 centimeters more. And ultimately, the fate would be that the whole of this plate A would be consumed, including the mid-oceanic ridge. Now, you will remember that at the start of the lecture I told you that some of the things we look at from 2D are counterintuitive. What the simple 2D velocity models and plate boundaries are telling you is how plate geometries are actually changing with time, right? They can change with time to the extent that plates can grow with time, plates can be completely consumed with time. It means that plates can disappear with time. So, even a mid-oceanic ridge can actually be consumed. Now, this is something that is counterintuitive. It is not the normal way in which we think of convection occurring. This is what happens. Now, for today, this is about as enough for this particular lecture for you to assimilate. So, I will skip through all of these and we will go on right to the conclusions of this lecture that we have had. So, the major takeaways from this particular lecture 6 is that the geometry of plate motions, we need to analyze it using the relative velocities between plates. We have no other alternative. Right now we have satellites, but at the time plate tectonics was devised in the 60s, most of the time we did not have enough satellite information. So, we had to use only relative velocities. Now, when depicting plate motions in 2D, divergent plate boundaries, they are characterized by relative velocity vectors, which must have a very significant component of their motion that moves away normal to the trace of the boundary. On the other hand, convergent boundaries would have relative velocity vectors that have a significant component of motion that moves normal to the plate boundary and it moves towards it, right. So, the catchwords here are away and towards. On the other hand, transform faults are characterized by relative velocity vectors that are parallel to the trend of the boundary. So, if you find that a relative velocity boundary vector between two plates is actually parallel to the trend of a boundary, it must have a significant component of transform motion. Now, we looked at it with respect to a simplified two plate system, and what we saw is that plate boundaries, they can actually move with time. As a consequence of the movement of plate boundaries with time, plates can grow larger with time, but they can also grow smaller, and sometimes they can even be entirely consumed. You might find a plate disappear completely from the surface of the earth. What we will do in the next class would be look at the junctions between three plates, because that is where you will find the most critical analysis of how plate geometries change on the surface of the earth can be understood. This is the reference that you can use for this, and thank you very much.